Good morning, students. In a previous class, that is class 1 of the chapter solid state, I already completed about what do you mean by solid, classification of solid, that is crystalline solid and amorphous solid, then classification difference between crystalline solid and amorphous solid. Next, depending upon the magnitude of force between the constituent particle, again classification of crystalline solid into ionic solid, covalent solid, metallic solid and molecular solid. Next, two terms, important term, crystal lattice and unity cell, then types of unity cell, then finally calculation of number of atoms present in a unity cell, then closed packing in one dimension and closed packing in two dimension. We know in two dimension there are two type of closed packing. One is known as square closed packing and one is known as hexagonal closed packing. So today in the class 2 of the chapter solid state, I will try to complete the three-dimensional closed packing. Next, packing efficiency, void or hole, then coordination number, radius ratio, calculation of density, and last one is imperfection or defect. So let us start one by one. First one is, that is closed packing in three dimensions. Mark that. That is closed packing in three dimensions. In case of three-dimensional closed packing, there are two different ways of closed packing. One is known as hexagonal closed packing and one is known as cubic closed packing. Mark that. This three-dimensional closed packing is of two types. One is known as hexagonal closed packing, that is known as HCP, and another is known as cubic closed packing, that is known as CCP. Let us discuss one by one. First one is hexagonal closed packing. It is difficult to draw the structure. That means this board is 2 dimension while I am giving an idea about 3 dimension. So sometimes we have to imagine the concept. So what is the arrangement? When the spheres are arranged in a row, then an edge or length is formed. Similarly, when the spheres are arranged in a column, then an edge or breadth is formed. So, when the spheres are arranged in a length and a breadth, then a plane is formed. When the different number of planes are arranged one after another, then another edge or height is formed. So this type of closed packing is known as three-dimensional closed packing. Generally, there are two types of closed packing. One is known as hexagonal closed packing and another is known as cubic closed packing. So point 1 discussed to, that is hexagonal closed packing. In case of hexagonal closed packing, the hexagonal cubic lattice, hexagonal cubic plane, when arranged one plane over another plane, then the constituent atoms present in the second layer lie in the depression of the first layer in such a way that the constituent atom in two different layers are aligned differently. When the third layer is placed over the second layer, Then it has been observed that the constituent atoms of the third layer perfectly aligned with that of the first layer. Mark that. The first one, that is hexagonal close packing, hydro, the spheres. It is of first layer. It is the second layer aligned differently. Then the third layer, mark that. The third layer which are placed over the depression of the second layer, then this alignment is exact alignment. So on the other hand, if the first layer is known as A type, second layer is known as B type, then third layer is also known as A type. So this type of arrangement, this hexagonal close packing, the type of arrangement 3 dimension, otherwise known as AB, AB, AB type of close packing in crystal system. Next, move to the second type, that is cubic close packing. In this system also, 3-dimensional close packing, when the second layer, hexagonal planar layer, is placed over the depression of the first layer, then the constituent atoms are aligned differently. Next, the third layer when placed over the depression of the second layer, then the constituent particles also align differently between the second and third layer. But when the fourth layer is placed over the third layer, it has been observed that the constituent atoms of the fourth layer is exactly aligned with that of the first layer. That means if the first layer is A type, second layer is the B type, and the third layer is the C type, then fourth layer is again of A type. So this type of arrangement in 3-dimensional system is otherwise also known as ABC type of arrangement. I repeat again, in case of hexagonal close packing, otherwise it is known as AB type of packing arrangement, while in case of cubic close packing, that is known as ABC type of arrangement. It is the little idea about 3-dimensional close packing. Next, Sujabatu, another word term, that is packing efficiency. What do you mean by the term packing efficiency? Next we discuss another term is known as packing efficiency or packing fraction. What do you mean by the term packing efficiency? The percentage of space occupied, the percentage of space occupied by the constituent particle in the crystal system is known as the term packing efficiency. I repeat it. That is the percentage of the space occupied by the constituent particle in the crystal system, or in the crystal lattice is known as packing efficiency. Experimentally, it has been observed that by calculation, packing efficiency for a simple cubic is 52.4%. In case of a BCC arrangement, it is 68%. And in case of HCP and CCP and FCC arrangement, it is of that is 74%. Mark that. Point 1. In case of simple cubic arrangement, the packing efficiency is 52.4%. The space occupied is 52.4%. Next, in case of BCC, body centered cubic arrangement, the packing efficiency is 68%. While third one, in case of HCP, CCP and FCC, in case of HCP, that is hexagonal closed packing, CCP cubic closed packing, and FCC face centered cubic closed packing, the packing efficiency is 74%. It is 1 mark question for multiple choice question or the fill the blanks question. What is the packing efficiency for FCC arrangement, for CCP arrangement, or for HCP arrangement? It is the little idea about what is packing efficiency, and that means what is the percentage of space occupied in case of different arrangement. Next we switch over to another one term that is known as void or hole. Next, we discuss the next term that is known as void or hole. What do you mean by the term void? In case of three-dimensional closed packing of the crystal system, when the spheres are arranged closest approach to each other, in between them some empty spaces left behind. I repeat again. In case of closed packing of the constituent particle in the form of spheres, it has been observed that there is some empty spaces left between them. That is known as void or hole. There are two types of voids are there. One is known as tetrahedral void and one is known as octahedral void. Let us discuss one by one. What do you mean by tetrahedral void? When one sphere is placed over three other spheres which are closest approach in such a way that between the four spheres some empty spaces left behind, that is known as tetrahedral void. And it has been observed that empty space is very, very smaller in comparison to the sphere. Mark that. It is the three spheres are there in the closest approach. Then if I draw the fourth sphere, imagine that the fourth sphere is placed over the third sphere, three sphere. Then some empty spaces in between the fourth sphere, which is known as the tetrahedral void. And that space, empty space, is very small in comparison to a sphere. Next is octahedral void. Similarly, this type of void is placed between the sixth sphere, three sphere at the bottom and three sphere at the top. In between the sixth sphere, the empty space is formed, that is known as octahedral void or octahedral hole. Mark that. I draw three sphere with a closest approach. Next also I draw 3 sphere in the closest approach. Mark that in between the 6 sphere, this vacant space form between the 3 sphere bottom and 3 sphere of the top. In between the 6 sphere, the space, empty space form, that is known as octahedral void or octahedral hole. Next we discuss another one term that is known as coordination number. Next we switch over to another one term that is known as coordination number. Next term is coordination number. In the shortcut, it is known as C dot N. What do you mean by the term coordination number? The number of nearest neighbor. The number of nearest neighbor of the constituent particle in crystal system is known as its coordination number. Mark that. It is defined as the number of nearest neighbor of the constituent particles present in a crystal system is known as its coordination number. I repeat again. The number of nearest neighbor of the constituent particle present in the crystal system is known as its coordination number. It has been observed that in one-dimensional closed packing arrangement, coordination number is 2. In two-dimensional closed packing arrangement, in square closed packing, it is 4. In hexagonal closed packing, it is 6. Mark that. Point 1. In case of one-dimensional closed packing, the coordination number is 2. Point 2. In case of two-dimensional closed packing, and in square closed packing SCP arrangement, C dot N is equal to 4, while in case of hexagonal closed packing, C dot N is equal to 6. Similarly, in case of three-dimensional closed packing system, in case of three-dimensional closed packing and in hexagonal closed packing and cubic closed packing system, coordination number is equal to 12, while in BCC, body centered cubic arrangement, coordination number is equal to 8. Very, very important one for 1 mark question, multiple choice as well as fill the blanks. We have to buy this one. That means in case of one-dimensional closed packing, any one sphere that is came in contact with two neighbor. That's why the coordination number is 2. And in two-dimensional square closed packing, one sphere surrounded by 4 sphere, that's why it is C dot n is 4. And in case of hexagonal closed packing, one sphere surrounded by 6 other sphere came in contact with neighboring 6 other spheres, so its C dot n is 6. While in case of three-dimensional closed packing, in HCP and CCP, the nearest neighbor, that is 12. While in case of body-centered cubic arrangement, the nearest neighbor is 8. Then moves to another one term that is known as radius ratio. What do you mean by the term radius ratio? Next we discuss another one term that is known as radius ratio. What do you mean by radius ratio? It is defined as the ratio of the radius of the cation to that of the anion. I repeat again. It is defined as the ratio of the radius of the cation to the radius of the anion. This value gives an idea about the coordination number and structure of that type of arrangement. And we know that in case of ionic crystal, the radius of the cation is always smaller than that of the anion, so the radius ratio value is always less than 1. Mark that. It is defined as the ratio of the radius of cation, symbol is r to the power plus, with that of anion, symbol is r to the power minus. That means radius ratio is equal to r to the power plus by r to the power minus. That means radius of cation divided by radius of anion. This ratio gives, next point, this ratio gives an idea about the coordination number and also the structural arrangement. The most important thing is that, I repeat again, since in case of ionic solid, the radius of the cation is always smaller than that of the radius of the anion, so radius ratio always less than 1. Now we go through a table to representing what are the possibilities of radius ratio, how it is related to coordination number, and also it gives the structural arrangement. Mark that. We build up one table representing how radius ratio relate with the coordination number, and also it represent the structure of that arrangement. Mark the table. That means first one is radius ratio, next one is coordination number, next one is structure, last one is example. Mark that. Point 1. If a radius ratio value lies between 0.155 to 0.225, then coordination number is 3. Structure is planar, triangular. Example is boron oxide. Mark that. Second one, if the radius ratio lies between 0.225 to 0.414, then coordination number is 4. It is tetrahedral, and example is zinc sulfide. Next, third point, if radius ratio lies between 0.414 to 0.732, then coordination number is 6. It is octahedral. Then example is sodium chloride. Last one, that is, if radius ratio lies between 0.732 to 1.0, then coordination number is 8. Then it is body-centered arrangement, body-centered cubic arrangement, and the example is cesium chloride. Mark that. This data gives a relationship between, if the radius ratio is known, it gives idea about the coordination number and the structural arrangement. Mark that. If the radius ratio lies between 0.155 to 0.225, then coordination number is 3 and it is a planar diagonal structure. Example is boron oxide B2O3. Next one, if the radius ratio lies between 0.225 to 0.414, then coordination number of this arrangement is 4 and structure is tetrahedral. Example is zinc sulfide. In the other case, if the range is 0.414 to 0.732, then coordination number is 6 and structural arrangement is octahedral. Example is sodium chloride. And last, if this radius ratio lies between 0.732 to 1.0, then coordination number is 8. Structural arrangement is BCC, body-centered cubic, and example is cesium chloride. Next, move to another one term, very important term, that is known as calculation of density. Next we discuss another one term that is known as calculation of density. Next term is known as calculation of density, symbol rho. How we calculate the density in a crystal? Density of a unit cell can be calculated by knowing the edge length and type of arrangement. Mark that. Density of a unit cell can be calculated by knowing the edge length and the type of crystal system. That means let the edge length symbolically represented as A in picometer and the number of atoms present in a unit cell is equal to Z. That means we know for simple cubic Z is equal to 1. For body centered cubic Z is equal to 2. And for face centered cubic Z is equal to 4. We have to remember this value. That means that's why the density calculation of density depends upon the arrangement. We have to remember, if it is a simple cubic crystal, then Z is equal to 1. If a body-centered cubic crystal, Z is equal to 2. And in case of face-centered cubic crystal, then Z is equal to 4. And another one term, the mass of an atom, next one is next term is mass of the atom, symbol is M, and Avogadro's number, symbol is capital Na, that is 6.023 into 10 to the power 23. By knowing this one, we have to calculate density of a unit cell, that is rho is equal to Z into M divided by Na into A to the power Q into A to the power Q into 10 to the power minus 30 gram per cc. Condition is that if that is edge length is equal to, edge length is given in picometer, then we have to multiply 10 to the power minus 30. If edge length is given in centimeter, then we write rho is equal to Z into M divided by Avogadro number into A to the power Q in gram per cc. I repeat again, two formulas there. If the unit of the edge length given in picometer, then we have to transfer in centimeter and multiply 10 to the power minus 30. While if the edge length is initially in the question given in centimeter, then we apply this formula, that is density is equal to Z into M divided by Na into Aq. Here M is known as the mass of the atom, Z is known as the constituent atom present in the arrangement in a unit cell. It is Z, it is 1 for simple cubic, 2 for BCC arrangement, and 4 for hexagonal, that is FCC, face-centered cubic arrangement. And Na or N0 is fixed, that is Avogadro number, and A is known as edge length. It is given in the question either in picometer or centimeter. Maximum time it is given in picometer. So by applying this concept, by applying this formula, let us solve one or two questions how this formula is utilized to calculate the density of a unit cell. Mark the question how this concept, that is calculation of density formula, is applicable for solving this problem. What is the question? An element with molar mass is 27 gram per mole form a cubic unit cell with edge length of, that is given 4.5 into 10 to the power minus 8 centimeter. If its density is given, then calculate the number of atoms present in the unit cell. Mark that. Answer. We know that the formula is rho into Z into M divided by Na into Aq. Here given the density is given, rho is equal to 2.7 gram per cc. Then edge length is given, that means A is given 4.05 into 10 to the power minus 8 cm. And for a sim, then this 2 is there. We know N0 Avogadro number 6.023 into 10 to the power 23. Then in case of simple cubic, that is Z is equal to 1. Putting this value, our M to calculate what is the number of atoms. Our aim is to calculate the Z. So Z is equal to rho into Avogadro number into AQ divided by molecular mass. So molecular mass is given, it is also given. M is equal to 27 gram per mole. Put this value is equal to rho given 2.7, Avogadro number 6.023 into 10 to the power 23. Mark that. I repeat again. Z is equal to rho density 2.7 into 6.023 into 10 to the power 23 into edge length, that is given 4.05 into 10 to the power minus 8 Q divided by molar mass 27. So on solving this value, mark that, on solving this value, the answer is 4. That means the total number of atoms present in the unity cell is 4. Move to second problem, mark that. What is the second problem? Silver forms CCP lattice. Answer. Given that is CCP cubic closed packing system is equivalent to FCC system closed packing system. That means given that Z is equal to 4 and edge length of the unity cell, that means small a, is equal to 408.6 picometer is equal to 408.6 into 10 to the power minus 10 centimeter. Next, molecular mass M is given, that is 107.9 unit. So our M, we know, calculate to density. Density is equal to Z into M divided by Avogadro number into AQ. Putting this value, we have rho is equal to Z, that is 4 into molar mass given, that means 107.9 divided by 6.023 into 10 to the power 23 into A naught edge length, that is 408.6 into 10 to the power minus 10 whole to the power 3. Mark that. On solving this one, the value, nearest value is 10.5 gram per cc. It is a little idea about for the calculation of density of a unit cell. Next term, that is imperfection or defect in solid. Up to the next point, that is imperfection or defect. Next we discuss, that is imperfection or defect in a crystal. What do you mean by the term imperfection or defect? Any deviation or disturbances in the regular arrangement of the constituent particle in crystal system is known as imperfection or defect. When there is some disturbances, when there is some disturbances from ideal arrangement around a point in crystalline solid, then that is known as buoyant defect. I repeat again. When there is a disturbances in the ideal arrangement around a point, then it is known as buoyant defect. Generally, this disturbance arises due to heat absorbed by the constituent particle or due to the presence of impurities. Mark that. Any deviation or disturbances in the regular arrangement of the constituent particles in crystal system is known as imperfection or defect. It arises due to heat absorbed by the constituent particles or due to the presence of impurities. Mark that. I repeat again. If there is any deviation in ideal arrangement of the constituent particle around a point, then it is known as, in a crystalline solid, then it is known as buoyant defect. Next, to discuss about the buoyant defect. This defect also classified into three types. One is known as stoichiometric defect, and one is known as non-stoichiometric defect, and third one is known as impurity defect. Mark that. Mark that. The buoyant defect again classified into three types. That is, point 1, stoichiometric defect. Point 2, non-stoichiometric defect, and third one is impurity defect. Mark that. This defect, when it is observed in case of deviation from the ideal arrangement around a point, that is known as buoyant defect. It is of three types. One is known as stoichiometric defect, next one is non-stoichiometric defect, and the third one is impurity defect.